Dear students, on behalf of SANDHAN program of Government of Gujarat, I, Samir Vaidya, from Department of Mathematics, Saurashtra University, Rajkot, will like to welcome you all. Today, in the lecture of mathematics, we will learn something in the subject of graph theory. The last 50 years have witnessed unprecedented growth in the research work in graph theory. The rise of computer era provided the reason for the development of this subject and the research in this subject. First of all, I will like to give you some of the historical background for this subject. The solution of Königsberg bridge problem in 1736 by the great Swiss mathematician Leonhard Euler is supposed to be the birth of graph theory. The Königsberg bridge problem is like this. The city of Königsberg in Prussia, which is renamed as Kaliningrad, was set on both the sides of the Prigel river and included two large islands which were connected to each other and mainland by 7 bridges. You can see the aerial view of city of Königsberg of that time. The problem was to find a walk through the city that would cross each bridge exactly once and reach at the same point. The islands could not be reached by any route other than the bridges, and every bridge must have been crossed completely every time. One could not walk halfway onto the bridge and then turn around and later cross the other half from the other side. Here, the aerial view of the Königsberg city and the situation of bridges and the Prigel river is shown in the first picture, while the situation of the Prigel river, its flow, and the 7 bridges connecting the 2 banks and the 2 islands is shown in the second figure. While in the third figure, the graphical representation of the problem given by Leonhard Euler is shown. And this graph is supposed to be the first graphical representation of the problem. The other milestones in the subject are like this. In 1847, theory of trees developed by G.R. Kirchhoff. In 1857, systematic definition of trees was given by Sir Arthur Cayley. In 1840, systematic presentation of well-celebrated four-color problem by F. Mobius in one of his lectures. In 1879, Arthur Cayley published a paper on four-color problem in first volume of Proceedings of the Royal Geographic Society. In 1920, a first book on graph theory was wrote by D. Koenig. In 1976, two mathematicians, Wolfgang Haken and Kenneth Appel, obtained an affirmative solution of four-color problem. Now, we will learn some of the basic definitions in this subject. What is graph? Graph G equal to V is a mathematical structure consisting of two sets. A non-empty set V, known as the vertex set, and a set E, known as the edge set. The elements of V and E are called vertices and edges respectively. Precisely, V and E corresponding to a graph G are also denoted as V of G and E of G respectively. Trivial graph. A graph with single vertex and no edges is known as trivial graph. In this figure, a graph which is a trivial graph with vertex V1 is shown. Null graph. A graph for which edge set is empty is called a null graph. Loop. An edge whose both the endpoints are same is known as a loop. Isolated vertex. A vertex which is not the end vertex of any edge is known as an isolated vertex. Parallel edges or multiple edges. If two or more edges have the same end vertices are known as parallel edges or multiple edges. Simple graph. A graph without loops or parallel edges is called a simple graph. Adjacent vertices. The vertices which are joined by an edge are known as adjacent vertices, and the adjacent vertices are also called neighbors. In this figure, a graph is shown. We can see that it is not a simple graph because an edge E6 is a loop. Edges E2 and E3 are multiple edges. Vertex V5 is an isolated vertex as no edge is incident on V5. Incidence of a vertex and edge. If a vertex is an endpoint of edge E, then V is said to be incident on E. E and V are called incident to each other. So, we can say that the relation to be adjacent is the relation between two vertices, and the relations of to be incident is the relation between a vertex and an edge. Some more definitions. Degree of a vertex. A degree of a vertex V of a graph G is defined as number of edges incident on V plus twice the number of loops. The degree of a vertex V is denoted by d of V or d of V of graph G. Pendant vertex. A vertex of degree 1 is called a pendant vertex. Odd and even vertex. A vertex of a graph is called odd or even depending on whether its degree is odd or even. Look at this graph. For the graph G, here the vertices V1, V2 and V4 are of degree 2, while the vertex V3 is having degree 3, vertex V5 is having degree 1. We can also observe that the vertex V5 is a pendant vertex and vertex V6 is of degree 0. We observe that no edge is incident on V6 and V6 is a isolated vertex. That's why the degree of V6 is 0. Now, we will learn the first theorem of graph theory. This theorem was also proved by the Swiss mathematician Leonhard Euler. The statement of this theorem is like this. For any graph G with E edges and n vertices, namely V1, V2 and so on Vn, the sum of degrees of vertices of a graph is twice the number of edges. Here is the proof of this theorem. Very simple proof. since each edge has two end vertices, each edge will precisely contribute 2 to the sum of degrees. Moreover, each loop will also contribute 2 to the sum of degrees, and hence the summation I equal to 1 to n dvi is 2 times the number of edges. It is a very intelligent result given by Euler. Immediately to this theorem, one corollary is there. Corollary says that for any graph G, there is an even number of odd vertices. Proof is like this. Let A and B be the set of even vertices and odd vertices respectively. Then for each A belongs to A, dA is even. This implies that sum of even number of terms is even, and that is why summation dA is even. Now, by the first theorem which we proved just now, we have the sigma dA plus sigma dB is equal to 2e, that is the total number of edges for the graph G, and thus summation dB will be 2e minus summation dA, which is even, being difference of two even numbers. As all the terms in summation dB are odd, the number of elements in B must be even. Thus, for G, there is an even number of odd vertices, which proves the corollary. Here, I will like to add remarks that it is always not true that a graph must have an odd number of even vertices, and for that we have to provide the two graphs. Look at the first graph. In first graph, there are 3 vertices of even degree, while in the second graph, there are 4 vertices of even degree, and that is why we